Today I'm going to walk you through Lab 7, and Lab 7 is about the two-story building. This is about multi-degree freedom system that we learned in ME 3333 systems and vibrations. So, um, so I trust that you already did your homework and you passed homework quiz and you listened to the lecture. Not necessary in that order. So let's see. The first task of this lab is to open the VI provided on Blackboard. So I think I almost have it ready for you. So this is two-story building project. There's only one project file. So you open that one. And then there's only one VI. So I open it. And then this one, this VI is exactly same as the one that you used for the homework. So task one says to examine it. Okay, so I think this is the base, this is the first floor, this is the second floor. In the simulation tab, I think I can this is a run simulation, exit, and then this must be for when I actually move the base. And enter A, B, C, D, and I can put in M1, M2, K1, K2, C1, and C2, and time plot. It's empty now. Frequency plot. Okay, frequency plot is the FFT, the fast Fourier transform plot of the time plot, okay, of the response. So this is your response plot in the frequency domain, and the Bode plot is a plot of they're plots of the transfer functions that I showed you in the lecture slides. Yeah. Okay, so now going to the task one, it says to open it, examine it, and I think I understand it. So here it says, to this VI simulates a general one input, two output, continuous time as a state space model. So this is a state space model. You have a states that are position, and velocity of the mass 1 and mass 2. And then this must be the A matrix, this must be the B matrix, where C sub t is the base motion. So that's your input to the system. And then output equation is not shown, but the outputs are just the position 1 and position number 2. So task 2 says considered M1 and M2 are same as M, and K, they're equal to each other, and K1 and K2 are also equal to each other. And then for K over M equals 270. Okay, so this number, I was withholding this number until now. So the ratio of the K to M is 270 for our lab setup. So identify A, B, C, D. So this is your A, this is your B, and C must be. Okay. Oh, I don't think I can write this in here, but let me see. I can certainly try. How about some scribble? Okay. So your output Y1 and Y2, okay, must be, okay, equal to some C matrix. But the thing is, your state vector is x1, v1, x2, v2, plus you have a D matrix times C. Okay. Ooh, excuse me. Okay. So Y1 is equal to Y1 is equal to what? X1. So you write down, oh goodness, I just want to type just some number in. Okay, it must be 1 0 0 0. Okay, that's the first row. Okay, that's the first row. Oh goodness. Okay, first row. Okay, and the second row, okay, I'm trying to copy. Okay. Oof. Okay, my Surface Pro does not have a lab view, so that's why I'm doing this. So now Y2 must be, don't worry, I just have to put in one more row. Okay, so this is Y2 must be 1 0 0 1 0. Okay, that's going to be your second row of the C matrix. Okay, so this is your C matrix, which I'm trying to grab and move. How is this? No. This is it. Oh, I got it here. Okay. Oh, I'm afraid to write this one, but for the D matrix, it should be just a 0 and 0, nothing. Okay, 0 and 0. Well, I'm gonna just leave it at that. Okay, that's good enough. Okay, so So now I think I identify my A, B, C, D. This is my A, this is my B, this is C, this is your D. Okay, and then those values, how are they being entered? Here it is. So go enter A, B, C, D. Oh, I can type them in here. Okay, we actually did it something better. Okay, when you run it, when you update, it will fill out those A, B, C, D for you. So what did I say by C? C was 1000, and then it was a 0010. It's all been calculated. It's just actually done for you. Okay, because you could have entered it this way too. You could just put it in yourself. Okay, but let's just do it this way. So let's see, exit program for now. And going back to the worksheet, it says we can examine the meaning of the modal frequencies and mode shapes, okay, using the free response. So we're not going to put in the base motion yet. So here it says omega first natural frequency is 0.618 times square root of k over m. I obtained this number in the lecture slide using MATLAB, okay, MATLAB. But if you actually look at the homework assignment sheet, it actually does the eigenvalue problem by hand. Okay, so you can look at either places to find the natural frequency. First natural frequency is 0.618 times square root of k over m. So now we're given this k over m. You know what that is. That's equal to 0.618 times square root of 270. So I'm got my calculator, and times 0.618. That's equal to 10.15. Okay, so your omega 1 is equal to 10.15 radians per second. While I'm at it, I'm going to divide by 2 pi to get the 1.62 hertz. Okay, so they're the same thing. Or F1 equals this. Okay, so it's actually a very precious number. I want to remember this number. So now let's go to, okay, the next line. This is the mode shape. So this is for the mass 1, this is mass 2. So these are the amplitude ratio of the mass 1 and mass 2 when it's vibrating at the first mode, okay, at the frequency of 1.62 hertz. So that means I can excite this mode. If I can excite this mode, okay, the first mode, and then it will be vibrating at 1.62 hertz with the amplitude ratio of 0.618 for the mass 1 and a 1 for the mass 2. Okay, so a little more for the mass 2. So now we can actually see this looking at our lab view simulation. Here it is. Okay, so I'm going to put in the initial condition. What was it? It was 1, and the next one was 1.618. Was that it? Let me check one more time. Ooh, it was 0.618 to 1. Okay, it's same thing actually. Okay, same thing. So if you look at the ratio of 0.618 to 1, that has the same ratio of 1 to 1.618. So sure, just to satisfy this, 0.618 and 1, and I'm gonna run it, and I'm gonna update. Okay, I have to make sure this is green, and then ABCD is all populated, and go to simulation and run. Okay, look, it starts from some initial location, and what happens? They're in phase. Okay, when the second floor is at its peak, and then a first floor is also at its peak. Okay, and then they move in the same direction. So, and it looks like it's losing amplitude, and it's all because of we have numerical error that's building up. So we could try the loop delay and the sample time. Okay, sampling time to be 1 millisecond. Go to, let's say, reset model, update simulation. Let's try. Okay, run. Okay, so I guess the motion will die out a little slower. Okay, but still, we still have numerical errors that's building up. Okay, so you can see they're all moving the same direction. Base is not moving. Okay, so let's stop for now. The next task. Okay, next task is so I think we just did the test 3. Okay, we saw the first mode of vibration. So this is what's depicting what we just saw in the simulation. The mass 1 and mass 2. Mass 1 and mass 2, they're moving in phase with each other, and then when the mass 1 has amplitude of 0.618, mass 2 has amplitude of 1, and they're at the 1.62 hertz. So we do the same thing, okay? We look at the second mode, and the second frequency, second natural frequency is 1.618 times square root of k over m. It's 270 and square root of that times 1.618 equals, I want to write that down, omega 2 equals 26.59 radians per second. Also equals f2 natural, second natural frequency is divide that by 2 pi, and then you get 4.23 hertz. Okay, and then we have a mode shape, the corresponding mode shape that has negative 1.618 and 1. Okay, then again, this ratio right there, the same as 1 to negative 1 to 0.618. Okay. So now this is the depiction of the second mode shape. So it says to repeat the task 3 in the simulation. So let's do that and go to enter ABCD. And then if I remember, this was negative 1.618 and there was 1. Sure, update SS model. Run. Oh, hang on, stop, reset. Okay, I should reset. Okay, I want one more. Okay, run simulation. Okay, what do you see? The first floor has bigger amplitude. Okay, when this is 1.618, this has a second floor has a amplitude of 1, and then they're 180 degrees out of phase. Okay, when the mass 1 is at its maximum, mass 2 at its negative maximum or the minimum. Okay. And then another thing, it's a pure sinusoidal function. It has only one frequency, and you want to see what the frequency is. And then let's look at just a little, oh, how about from here to here? Okay, from here to here. So let's see. The one period is from here to I'm looking at the red one, the first floor, from here to right there. Okay, and that looks to be about 0.24 second. So let's see what's 0.24 second is. 0.24 second and inverted, it's about 4.17 hertz. Okay, so that's close, very close. I mean, if I use more than 1 cycle, I'm sure I would have gotten 4.23 seconds. Okay, but that's close enough for now. So you can see this is pure sinusoidal motion with pure harmonic motion with frequencies at 4.2 hertz or so. So let's continue with the worksheet. So task 4, we just did the task 4. We saw the second mode shape. So let's choose the initial condition that is not one of the two mode shape and verify that the response is a superposition of the two modal frequencies and the shape is not a mode shape. So I actually thought about this quite a bit. So enter ABCD, and what I want to do is I want to put in, positive 1.618 and 1. Okay? So this is this doesn't look like any of the mode shapes, right? Okay, so let's see. So if I go to simulation, right? What's the first mode shape? First mode shape is when this one's 0.618 to 1, right? So I made the first mass go out further out, and mass 2 not as much. So simulation, will this work? Hang on, I should have reset the simulation. Update and go run. Here it is. Okay, so when you look at this, you see, look at this funky shape. Okay, what is it happening? Okay, I need to stop. I want to reset. Okay, I just want you to look at it before. Okay, before damping is too much, then you lose that transient response. So update simulation. Let's do it again. Okay, look at this. Okay, it's got an overall motion of like going to the right. The whole thing is moving to the right and left and right, left. And then in the meantime, you have a high frequency component. Okay, they're wanting to go opposite direction. Didn't make any sense at all. Should I try one more time or move on? Okay, so what I'm trying to say is that was a superposition of, okay, whether you believe me or not, that was a superposition of two frequencies with two modes, and then when you just look at that, it's very hard to tell, okay, that it was just made out of two sinusoidal functions. So when you look at the frequency plots, that's the FFT of the time plot, which I don't think I have enough of I don't think it's good. Oh, it did work. Okay, I guess I had enough data point. You can see, okay, FFT plus shows you the two frequencies, and the first frequency is near, it's between 1 and 2, 1 and 2, sure, 1.6. I think I need to zoom in if I want to actually look at that. And then this one is that this is 1, this is 9 is 2, this is 3, and this is 4. Between 4 and 5, but closer to 4, you see the response as these two frequencies. Okay, even if your bare eye, if you can't tell just by looking at it, FFT, if you do FFT, you can see they're clearly two dominant frequencies, and they're the two natural frequencies. So I'm convinced. I'm convinced there are two frequencies. So now what's next? So okay, so now test 6 is a set the damping ratio to a small number, zero point 0. I don't think I need to. I don't need to because we already have numerical damping. So sure, okay. So sure, so I'll do it. Okay, I'll do it. So zeta is equal to 0.01, and then just determine C. Okay, so right now we're setting M to be 1 because we really don't know the mass. Okay, we only know the ratio of the K and M, but we don't know the individual mass or the spring constant of that, the leaf spring. So specify C. Okay, so that means C over 1 equals 2 times zeta times omega 0, where omega 0 is defined to be just the square root of K over M. So I have 270 square root, so that's omega 0 right there, and times zeta 0.01, and times 2 is 0.328. Okay, so I'm going to put 0.328. The frequencies, I need to write this down. So 0.5, 1, 1.5, 2, 2.53, oh, 3.5, 4, okay, why didn't I just say the 0.5 through 0.5.5? Okay, so I'm almost ready. Okay, so now I want to actually exit program, go to simulation. I'm going to actually go back to 5 milliseconds, 5 milliseconds, and with the ABCD, C is 0.328. It was actually 0.3286, so I'm just gonna put 9. Okay, okay. So, and then go to simulation, and I'm gonna put in frequency of 0.5. Okay, phase is 0. You actually have to put in 0, enter. And for the amplitude, what kind of amplitude would you like to put in? This is actually in meters or centimeters or millimeters. So I actually want to put in 1. Okay, 1. Okay, so I want the base to move plus minus 1. Let's see if it works. So right now, from task 6, we are not looking at the free response anymore. Yeah, we want to look at the response when the base is moving. So we want the transient response to die as soon as possible. So we want it to be realistic. So we put in the 1% damping. Okay, we didn't want to put in like the we didn't put in like too much damping. Okay, so I mean the actual system is lightly damped. So 0.01 zeta equal to 0.01 is a very realistic number. So let's see. Enter ABCD. So initial conditions, I can just set this to 0. I don't think because we don't even want to look at the transient response anyway. And then go to update and go to simulation, and then OK, and I'm gonna run. Okay, so this is a case where the base is moving slowly. Okay, with a frequency of 0.5 hertz. Okay, it goes back and forth once every 2 seconds. Okay, and then we do have some response, right? Transient response, but we just let it run for a long time. Okay, long time, and see what happens. Yeah. So this is the response that we can see from the Bode plot. Remember the Bode plot that only has to do with the particular solution, not the homogeneous solution. But all the homogeneous solutions is disappearing. They're all it's why? Because it's an asymptotically stable system. So right now, this is your steady state response, or same as a particular solution. So let's see, I can like stop for now, and then I'm gonna check the worksheet one more time. Okay, so it says for each case, let the transients die out, then record the amplitude ratio of each floor to the base and the phase difference between each floor and the base. Okay, and compare these results to the magnitude and the phase characters shown in the figure 6. Okay, and figure 6 is your Bode plot. Okay, so I did something a little bit better. Okay, so now I can close down this document, and I'm going to show you some other document that oh my goodness, Google current courses. I'm sorry. Okay, assignment. Oh, actually, not that one. Okay, this one with the worksheets, and then the worksheet table. Here it is. Okay, I did something better for you. Okay, so which is I have a transfer function. Okay, T1 and T2, and we introduce another frequency which is called the eta. Okay, eta is a normalized frequency where eta equals to omega divided by square of k over m. Why do we use this? Because we do know that natural frequency is at 0.618, and the second natural frequency in terms of eta is at 1.618. Okay. So it's just easier to look at the body plot and then compare. So now these numbers, all these numbers are calculated numbers, okay, based on this body plot. Why? Because I already have an expression for the transfer function 1, transfer function 2. I don't have to look at the body plot. I can just directly put in the eta frequency for the zero point 0.5 hertz, zero point 0.5 hertz. I can calculate the omega, which is 2 pi f. So 2 pi times zero point 0.5 will be 1 pi, and then 1 pi divided by square root of 270. So that's my eta, 0.19. Okay, so when I have a 0.19, I can plug this number into transfer function 1 for the first floor and transfer function 2 for the second floor. So I plug those in, and then with a pure ratio, okay, not decibels, as a pure ratio, so plug in 0.19 instead of s equal to I times 0.19, and plug it in, find the amplitude, and you have a 1.08, and then you have a phase will be 0 degrees. And then for the second transfer function, if you plug that number into second transfer function, you get the magnitude of the 1.12. What does that mean? That means that this is the amplitude of if the base is moving plus minus 1 unit, your first floor will be moving plus minus 1.08, okay, unit, and the second floor a little more, okay, 1.12 plus minus 1.12. So these numbers are calculated for you. So I'm going to compare the calculated number with what we get now. Okay, so let's see, going back to the worksheet. Okay, going back to the worksheet, I'm supposed to fill out, or you're supposed to fill out this table right here. Okay, I am ready. Okay, so I'm gonna move this out of the way. Okay, I'm ready because I'm gonna look at the time plot now. Okay, I'm going to look at the time plot now, plot it, and I'm going to look at the top, just a little bit of it at the top. Okay, see, when the base is moving, when the base is at 1 unit to the right, floor 1 is at 1.08 and the other is 1.12. Okay, I'm going to type those in. Oh, where's my I'm gonna type those in. Okay, I'm ready. So this one, it doesn't change. This is still 0.19, and the first floor, not dB. Okay, I want to actually get rid of that one. So 1.08, and the degrees will be 0 degrees. Do you see any phase difference between the input and the output? They peak at the same time, almost nearly at the same time. So 1.12, this will be 0 degrees. Okay, so I'm done with the first entry. Let's exit program. I'm going to go to simulation, and I'm going to do the same thing for 1. Okay, so it can get a little bit boring, so what I'm going to do is I'm just going to pick maybe 4 frequencies. So let me do, which one should I do? Which one should be interesting? Let me do the, okay, so this is, I mean, I already have an answer to my questions. So let's see, let me try. How about 1.5? Okay, 1.5. So I'm gonna put in 1.5. So this is the third entry. Amplitude is still 1. So I'm gonna, okay, I'm gonna start running and go to ABCD, update simulations, and go to simulations and run. Okay. So so now this is when you're very near resonance. right? The natural frequency is 1.62, and then the floor is oscillating at 1.5 hertz. So this is actually quite dramatic when you look at this in the lab, and then it's loud, and and then it could be quite scary. So this is when I probably just stop, use the emergency stop button. So let's see. I can stop. I can go to time plot, right? And you see a little bit of beating, okay? And then my settles, okay? Settles. So now let's look at very last one, okay? So what do you see? You see the first floor is at about 5.2. So I'm going to put that number in, okay? 5.2. And the second floor is about 7.2 also. Okay, so this is a third one. So this number should be 2 pi times 1.5. You change to omega, right? So 2 pi f, and then you have to divide by square root of 270. So that's your eta frequency, which is equal to, I'm gonna cheat from my sheet, okay? So that's equal to 0.57. Okay, that number should be 0.57, or simply it's like 3 times the eta 1. And the first floor, the ratio it's not in dB, okay? Remember, it's at 5.2, and it's nearly 0 degrees, okay? I mean, I think I can live with the 0 degrees. And then second floor is a 7.7-ish, okay? 7.7 and 0 degrees. Okay, so if I look at my own numbers that I calculate from the transfer functions, these are the numbers: 5.53 and 8.25. Okay, it's a little bit different. Okay, it's a little bit different. I mean, remember, this is a numerical simulation, right? Okay, can't be perfect. So now exit program again. So which one is gonna be interesting? Let me think. Okay, the one frequency that's going to be really interesting is what's called the zero frequency, when omega is at square root of k over m, which is 270 square root, that's 16.4 radians per second, and you divide by 2 divided by pi, you get frequency of 2.6. So I'm going to put in 2.5, 2.6. I'll just put in 2.6. So I'm going to run it, enter ABCD, update, go simulation, run. Yeah, so right now we have some change in response, still dying. So this is an interesting case. Why? Because when you look at mass 1, it's barely moving. Okay, so this is the frequency that when you look at the Bode plot, you're right here. Okay, you're right here where the amplitude for the mass 1 is like negative, very large number decibels. So that's essentially 0. Okay, so if you look at the time plot, I'm gonna look at it. So your amplitude ratio for the mass 1 is 0.1, and go back. And for the mass 2, it's nearly 1. Okay. And how about the phase angle? So let me go back to a different plot. Okay, let me cover the whole range. Okay, so I'm ready to talk about the phase. So here it is. Okay, for the mass 1, the peak occurs here where the peak and the input occurred right here. Okay, so I always want to look to my right. Okay, so this is my base motion, this is my input, and I always want to look to my right. Okay, look to my right. Okay, because I want to talk about the phase leg instead of phase lead. So here the peak occurred about 11.5, let's say 4 seconds, 11.54 seconds, and then let me see. And then the peak and the output occurred at 11.65 seconds. 11.65 seconds. So the difference is about 0.11 second difference. That's a time lag. Okay. So change to phase, what you do is you divide this number by the period. So what's the period? So, I mean, I think we can calculate this because I put in 2.6 hertz input. Let me check. Okay, I put in 2.6. Okay, really 2.6 hertz, and change it to period. So 2.6 hertz, and then divide by that. So the period is 0.33846 seconds. Okay, so now I'm just gonna use the ratio. So I have 0.11 second of time lag, and then divide by 0.3846 second of the period, and you get about 0.3286. That's a fraction. Okay, so 28.6%. So what you do is now you multiply by 360 degrees. So that's like 103 degrees. So that's the phase lag. You have a phase lag of 103 degrees. How about for the green line? Okay, you can see this is almost like upside down graph, right? The green is almost upside down of the white graph, which is the input. So this is about 180. So I'm ready to fill in the blanks. Let's see. Okay, for this number, so I actually use a 2.6. Okay, and then here the first floor was about zero point 0.1, and then degree was negative 102 degrees, 103 degrees. And second floor was about 1, okay, 1.0, 1.01, 1.01, a little bit greater than 1, okay, and then angle was negative 180 degrees or positive 180 degrees. It's the same thing, but we tend to use negative number. Okay, so these two numbers, okay, this number especially, okay, you couldn't have figured it out using the transfer functions, the one that is at least the one that I gave you. Why? Because those transfer functions, for simplicity's sake, the damping was set to 0. Okay, so these clearly, I mean, there's a number between 0. When you look at body plot, there's no angle between 0 other than 0 and 180 and 360. Okay, but right now we're at around here. Okay, around here. So this is your transitioning, the angle transitioning from, for the first floor, from negative 180 to 0. So we caught somewhere between 0 and negative 180 around here. And for the second floor, the phase angle is staying at negative 180. So that's why when you look at this, it's at 180. Okay. So let's see, exit program. So we continue. Okay. So we continue, with experiment. So where are we? Right now we're at around here. Okay, so should I continue with the 3? I'll just do maybe 2 more. Okay, I'll do 3, which is between the 0 frequency and the second natural frequency, and I'll do 1 more at 5.5. So I'll do 3. So, okay, why not? So go to simulation, I'll put in 3, and I do okay, stop simulation. Let me do it again. Update, and then I'll go run. Okay, so we have to wait until the transient response dies out, and it has to become pure sinusoidal function at the input frequency. So we see 3 frequencies. If you look at frequency plots and then you go frequency plots, you should see like 3 frequencies. One of them should be at first natural frequency 1.6, and second natural frequency 4 point something, and the third one, which is at 3 hertz. Okay, 3 hertz. 1 2 3, 1 2 3. So you see 3 hertz right there. Okay, and then you don't actually see the second natural frequency right now. Why? Because higher natural frequencies are harder to see in the response. So look at the time plot. Okay, I'll say this is good enough. Transient response has died out, and let's look in here. Okay, let's look in here, and let's see. Should we look at the? Oh, I didn't mean that. Okay, let's look at the gain first. Okay, so 0.28 for the first mass. Okay, so this is 0.28 for the first mass, And then for the second one, amplitudes are much easier to get. So let me do amplitude. Oh goodness, I mean this. Okay, point 0.8. Is point 0.8 good enough? Okay, it's good enough for me. So point 0.8. So 0.8 and 0.8. Okay, now let's try the phase. So I'll be happy if we can get the phase within plus minus within 90 degrees. Okay. So what do? What I usually take out a piece of paper. What do you mean? What do you mean, Dr. Han? Okay, so what I usually do is I take out a piece of paper and then just measure the distance from here to here. Okay, I don't even do a ruler, just in the mark it on the paper. Okay, then what I do is from here to here, okay, from peak to peak, okay, from input to the output number one, okay, I look at the distance between those two. Okay, so when I look at it, I'll say this is maybe 1/10. So distance from here to here is 1/10 of distance from here to here. That's a total guess. Okay, so it's a 1/10 of 360. See how simple that is? Okay, I don't need a piece. I just need a ruler. Okay, not even a good ruler. I just need a piece of paper so I can mark it and eyeball it. So that's about negative. I'll just say negative 36 degrees. Yeah, good enough. Okay, so now for the second floor, which is the peak is right here. This is you only look at the peak right after the input peak. Okay, so distance from here to here, I'll say that's like half, a little bit more than half maybe, of the total period going from here to here. That's a total period. Okay, the distance from here to here is about maybe about half. Okay, so now that's half of 360 degrees. So that is 180. But I'm just going to use negative 180. Negative 180 same as positive 180, right? It's negative because you're looking at the peak coming after, okay? After the input peak, okay? So that's when you have 3. So you wanna know the real number. If you look at again, okay, the calculated values are based on no damping. Okay, so this number is about exact number is 0.26 when damping is 0, and this one 0.8, the exact number is 0.822. Okay, exact phase here is a 0, and then that's negative 180. Okay, the difference between the calculated values and the experimental values, that in the experiment we do have a little bit of damping. Okay. So let me do one more. Ooh, the 4.5, I shouldn't measure anything, but let me just show you what 4.5 looks like. So exit program 4.5. So this is very near the second natural frequency. So let me run it, enter ABCD, update, and run it. Okay. So this is the probably the most dramatic case we have in the lab. Yeah. Why? Because look at the base goes to the right, mass 1 goes to the left, and mass 2 goes to the right. They're all 180 degrees out of phase. And not only that, this is so near the second natural frequency that it can get really loud. One thing to note, okay, it's actually very, even though your body plot can predict infinite amplitude, but it can't. Okay, it can't. Okay, okay. So why? Because we have damping, yeah, and it doesn't. Okay, it doesn't go to infinity, and not only that, this width turned out to be actually narrower. Okay, narrower than the width for the first resonance. So it's actually hard to get the large amplitude vibration for the higher modes. So this is when you have the frequency of 4.5. So let me do one more when it's at 5. Okay, when it's at 5, so this is to the right of the second natural frequency. So let's go to ABCD update simulation. Oh, maybe I should reset. Okay, run. So wait a little bit until the transient response dies out. Look at this. First and the second out of phase. Second and the third out of phase, right? And the base and the base and the second floor, they're in phase. I mean, can you see that? Just looking at the time plot, right? The base and the second floor almost in phase, base and the first floor, these two out of phase, right? Okay, so you can see this. And then if you look at the Bode plot again, okay, Bode plot again. So right now you're in this range. Okay, what does it say? The first floor 180 degrees out of phase with the base, and the second floor 360 negative 360 degrees out of phase with the base. That means they're in phase. Okay, that's what it says right there. Okay, so let's exit program. So so I just want to go over one more. Okay, one more thing. So just looking at the phase, okay, looking at the relative phase between the mass 1 and mass 2, you can actually almost tell where you are, okay, in this region. Okay? So if you see that if you're mass 1 and the base are in phase, but the base and the mass 2 are out of phase, you know right away this is the frequency is just below the second natural frequency, but above the what's called the zero frequency. Okay, and just in case, because I can't remember if I did the case or not, let me show you. Okay, so this is when you have simulation. So this is between 4.5 hertz and 2.5. Can I just do 3? Oh, that sounds familiar, actually. Okay. So what should happen? First two, base and the first floor, they should be in phase, roughly in phase, but the first and the third should be out of phase. Okay. And okay, we have to wait a little longer. Almost, almost. Okay, can't wait any longer. Here it is. Okay, when the base is at positive max, the floor one is almost at the positive max too, right? If I look at this, look at the second floor is at the negative maximum position. So these two are 180 degrees out of phase, right? By just looking at the phase, right, I know that, oh, the input frequency must be where? Must be where? Between here and here. Okay, so anyway, so that's what's to come on the quiz. Okay, you should be able to tell just looking at the phase plot, okay, and the response. You should be able to tell what where the input frequency should be. Okay, and now you're ready to take the quiz 7. Okay, thank you, and then this is it, and I guess I'll see you again for lab 8, the final lab.